Hello, I'm going to tell you about the generation of negative frequency resonant radiation in an optical fiber. We observe every stage of the generation using the chirp of the generating pulse. First, let me explain what we mean by negative frequency. If we express the electric field in complex form by Fourier transform, we routinely use negative frequency. However, the negative frequency field is predetermined by the positive frequencies and vice versa. Negative frequencies seem redundant. In our experiment, we are coupling the positive and negative fields in a unique way, demonstrating the physical reality of negative frequencies. For quantum fields, it is established that negative frequencies correspond to the amplitude of the creation operator, and positive frequencies belong to the annihilation operator. In this setting, the coupling between positive and negative fields generates photons. So how do we couple positive and negative frequencies? Look at the wave equation in a nonlinear medium. We use a one-dimensional scalar model, offset frequency and wave number by the carrier, transform to a frame moving at the group velocity of light in the medium, and Fourier transform in space and time. Rewriting the equation as a linear and a nonlinear part, we can view this as an oscillator driven by the nonlinear polarization. Where the linear dispersion exhibits a zero, the oscillator is resonant. This resonance can be expressed as a momentum or energy conservation in the lab or moving frame. In any case, we observe that in addition to the trivial solution of the driving field, there is one positive and one negative frequency resonant radiation solution. The well-known positive resonant radiation has been observed before and is associated with short pulse tunable visible light generation. It emerges if a pulse in the fiber broadens spectrally far enough to excite the resonance. Similarly, for negative radiation, the pulse has to broaden so far as to reach the resonance. Here you see the simulated spectral evolution of an intense pulse in the fiber. You can see the significant spectral broadening over more than an octave. In our experiments, we use the input pulse chirp to delay this violent spectral broadening along the fiber and to observe the spectra of negative resonant radiation at every stage of pulse evolution at the end of the fiber. Finally, these are the spectra of negative resonant radiation in the ultraviolet. For large chirps, there is no radiation as the pulse spectral broadening is delayed beyond fiber end. For lesser chirps, we see tremendous spectral broadening into the ultraviolet, which is generating the negative resonant radiation. For even lesser chirps, we see the pulse spectrum contracts again, leaving behind the generated resonant radiation. For close to zero chirp, no radiation is observed because of fiber losses. In summary, these experiments shed light on the existence of negative frequencies and allows us in detail to study pulse compression in a nonlinear medium. Further details, such as the optimal chirp for pulse compression and the characterization of fiber loss, you will find in the paper. Thank you.